Hello dear students, how are you? Today I am going to explain the topic Valency shell electron pair repulsion theory. This topic is mainly useful to identify the shapes of the molecule, and this topic is very important for the application type of questions in the competitive exams. So now we are going to discuss the topic Valency shell electron pair repulsion theory. So this is the Valency shell electron pair repulsion theory and we are going to discuss. So what is Valency shell electron pair repulsion theory and how it is useful? What information it will be give? So that entire topic will be discussed clearly step by step. So now generally if you see the molecules like CH4, NH3 and H2O, these are the three different molecules. These three different molecules, when you are writing the structure, you can observe that different bonds and different lone pairs you can observe. Now the Valency shell electron pair repulsion theory gives the information about the shape of the molecule. It gives the information about the shapes of the molecule. Means CH4 what is the shape, H2O what is the shape, and NH3 what is the shape. So this theory gives the information about the shapes of the molecule very clearly. This will be worked out 100%. So Valency shell electron pair repulsion theory gives the information or gives a clear information about the shapes of the molecule. At the same time, one more concept you have to discuss here about the hybridization. So hybridization will be give the information about the geometry of the molecule, and this theory gives the information about the shape of the molecule. One is geometry, one is shape of the molecule. So Valency shell electron pair repulsion theory gives the information about the shape of the molecule. That means we can determine the shape of the molecule. With the help of hybridization, we can determine the geometry of the molecule. With the help of the Valency shell theory, we can determine the shape of the molecule. With the help of hybridization, we can determine the geometry of the molecule. Then what is the difference between the geometry and shape of the molecule? Is any relation is there? Or if it is different, how it is different? That we have to discuss here. So geometry we can determine with the help of hybridization. If you know the hybridization of the molecule, we can determine the geometry or we can predict the geometry. Depend on the hybridization, either sp hybridization, either sp2, sp3, sp3d, sp3d2. Depend on the hybridization, we can say the geometry. But shape of the molecule, we cannot say depend on the hybridization. So it will be depend on different conditions. So let us see here. First, hybridization. How can you identify the hybridization for a given molecule? So the formula to identify the hybridization, Z is equal to half into number of valency electrons of central atom. Whatever the molecule we are taking, in a molecule central atom present and the central atom having valency electron. So number of valency electrons of central atom minus positive charge. If any molecule having positive charge, for example NH4 plus, and next of all what CO3 minus 2 minus charge, NH4 plus positive charge. If any molecule having positive charge, how many positives are present, that you have to write here. That is minus positive charge, because positive charge nothing but what, electrons are losing. So number of valency electron, from the valence electron how many losing, that means minus. And next of all plus negative charge. Negative charge nothing but when a atom get the negative charge when it is accept the electrons. So Cl minus electron is accepted. Next one CO3 minus 2 nothing but 2 electrons are extra. So extra nothing but valency electron plus the 2 extra electron. So that is plus negative charge. At the same time plus number of monovalent atoms. Number of monovalent atoms. Then what is the monovalent atoms? The atom which is ready to form the one bond. That is simply we call as a monovalent atoms. So generally what you can observe here, hydrogen, fluorine, chlorine, bromine and iodine. Generally we can say these are the monovalent atoms. So now based on this formula, we can identify the hybridization of a molecule. Either the molecule is sp, either the molecule is sp2, either the molecule is sp3. Whatever the hybridization, we can identify by this formula. So let us see, for example, I am taking CH4. CH4 I am taking NH3 and H2O. These three, CH4, NH3 and H2O. For example, I am taking these three molecules, CH4, NH3 and H2O. So I am going to identify the hybridization of these molecules. Let us see here. CH4 Z is equal to half into number of valence electrons, how many? Carbon. Number of valence electron carbon is 4, because valency of the valence electrons in carbon, how many? 4. So how can you identify? For example, carbon atom number is 6. Electronic configuration 1s2, 2s2, 2p2. So now valence shell of the carbon, how many electrons are present? 4 electrons. So that's why carbon valence shell 4 electrons are present. So number of valency electrons in carbon 4. So it means Z is equal to half into number of valency electrons of carbon. How many? 4. Plus any positive charge is present? No. Any negative charge is present? No. But what is present? Monovalent atoms are present. Monovalent atom. How many monovalent atom? 4. So that means 4 plus 4. 4 plus 4 is 8. Up into 8 nothing but 4. So the value 4 nothing but hybridization we can determine as a sp3. Hybridization is sp3. Next come to the NH3. Nitrogen and 3 hydrogens. Nitrogen, 5th group of element, mean valence shell 5 electrons are present. Plus number of monovalent atoms 3. 5 plus 3 8 and 8 by 2 nothing but again 4. We can determine this is also sp3 hybridization. Come to the H2O. Oxygen group number is 6. That means valence shell 6 electrons are present. Then half into 6 plus there is no positive charge, there is no negative charge. But monovalent atoms present. How many monovalent atom? 2. It means 6 plus 2. Half into 6 plus 2 8. 8 by 2 nothing but 4. Again it is also sp3 hybridization. So now hybridization we confirmed. H2O sp3 hybridization. NH3 sp3 hybridization. CH4 sp3 hybridization. Hybridization if it is sp3, the geometry of the molecule is tetrahedral. Hybridization if it is sp3, then the geometry of the molecule is tetrahedral. That means CH4 geometry tetrahedral, NH3 geometry tetrahedral, H2O geometry tetrahedral. 3 different molecules also having same geometry. What is that? H2O tetrahedral, NH3 tetrahedral, CH4 also tetrahedral. So we can identify the geometry. Geometry we can determine with the help of hybridization. Hybridization is sp3, because of that geometry is tetrahedral. Hybridization and geometry is clear. Next we are going to discuss about the shape of the molecule. So how can you determine the shape of the molecule? So according to valency shell electron pair repulsion theory, a molecule if it is having any lone pairs on the central atom, if a molecule a central atom, if it is having lone pairs, the lone pairs occupying more space, lone pairs occupy more space compared to bond pairs. Lone pair occupy more space compared to bond pairs. According to VSEPR theory, lone pairs occupying more space compared to bond pairs. Then what is the mean of lone pair? What is the mean of bond pair? So for example, if I am taking H2O, H2O nothing but oxygen and 2 hydrogens are present. Oxygen atomic number is 6. When I am writing the electronic configuration, oxygen atom number 8. When I am writing electronic configuration, 1s2, 2s2, 2p4. This is the oxygen electronic configuration. Valency configuration is 2s2, 2p4 because last shell. Now 2s how many electrons are present? 2. 2p4 how many electron present? 4 electron. First electron, second electron, third electron, fourth electron. Totally 4 electrons are present. So when 4 electrons are present here, in these 4 electrons, 2 electrons are unpaired and 2 paired electrons are present. According to valency bond theory, unpaired electrons only participating in the bond formation, but lone pairs does not participating in the bond formation, or paired electron does not participating in the bond formation. So this is a paired electron, it is a paired electron. These 2 pair of electron does not involving in the bond formation, but these 2 will be involving in the bond formation. So now how many electrons are involving in the bond formation? 2 electrons are involving in the bond formation. The remaining 2 pairs does not involving in the bond formation. So the electron pairs which is not involving in the bond formation, that we call as a lone pairs. So first lone pair, second lone pair. These two electron pairs not involving in the bond formation. The electron pair which is not involving in the bond formation we call as a lone pair. The electron pair which is involving in the bond formation we call as a bond pair. This is the lone pair and bond pair. So according to Valency shell electron pair repulsion theory, lone pairs occupy more space compared to bond pairs. Why lone pairs occupying more space mean? Lone pair is attracted by one nucleus, but bond pairs are attracted by two nucleus. Let us see again same. H2O, this is the lone pair, these are the bond pairs. Lone pair nothing but what? This is. Bond pair, this is. Bond pair nothing but two electrons are present. Out of two electron, this electron attracted by oxygen, this electron attracted by hydrogen. A bond pair nothing but two electron. Out of two electron, one electron attracted by oxygen, one electron attracted by hydrogen. It means bond pair nothing but it is attracted by how many elements? Two elements. So bond pairs are attracted by two elements or two nucleus. But lone pair, this is the lone pair, right? This lone pair is attracted by only one nucleus. At the same time here two electrons are present. Two electrons are attracted by only one nucleus. So it means it is occupying some more space compared to bond pairs. So lone pairs are occupying more space compared to bond pair. When it is occupying more space between these two, repulsions are very more. When it is present in this situation, between these two, repulsions are very more. Because it is occupying more space. When it is occupying more space, it will be very close to each other. When the two electron pairs are very close to each other, what happens? The repulsions are very more. So according to this one, Valency electron pair repulsion theory, lone pair to lone pair repulsion is very more compared to lone pair to bond pair and compared to bond pair to bond pair. Repulsion is very more. Where it is very more? Lone pair to lone pair, the repulsion is very more. Compared to lone pair to bond pair and compared to bond pair to bond pair. So now this is the repulsions order. This is the repulsions order. So now if we see that because of the repulsions, so we can understand only how many bond pairs are present, how many lone pairs are present here. Due to this repulsion, we can determine the bond angle also. So bond angle changes in different molecule because of the repulsions. So that is different topic. We are discussing about the shape of the molecule. Shape of the molecule according to Valency shell electron pair repulsion theory, shape of the molecule is regular. Shape of the molecule is regular when the central atom, shape of the molecule is regular when the central atom has no unpaired electrons or no lone pair electrons. When in a molecule, if a central atom does not have any lone pair, at that time the shape of the molecule is regular. It means when a molecule does not have lone pair, only bond pairs are present, zero lone pairs are present. At that time, geometry and shape of the molecule is same. Geometry and shape of the molecule is same when zero lone pairs are present. If lone pairs are present, one or more than lone pairs are present, if lone pairs are present, then geometry and the shape of the molecule is not equal. If lone pairs are present, geometry and shape of the molecule is not equal. If lone pairs are not present, then geometry and shape of the molecule is equal. If the lone pairs are present, then the geometry and shape of the molecule is not equal. So now CH4 we discuss. CH4 does not having lone pairs. At that time, the CH4 geometry and CH4 shape both are equal. It means CH4 geometry tetrahedral and shape of the molecule also tetrahedral. If lone pairs are present, what happens? The geometry and shape of the molecule is different. So let us see. So if it is different, what type of shapes will we get? So now we are discussing about the CH4, H2O and NH3. CH4 structure, this is 4 hydrogens are present. And next one is NH3, 3 hydrogens and 1 lone pair is present. Next one H2O, 2 hydrogens and 2 lone pairs are present. CH4, 4 bond pairs only but 0 lone pairs. A molecule central atom does not having lone pair. At that time, geometry and shape of the molecule is equal. So here geometry tetrahedral At the same time, shape of the molecule also tetrahedral. Shape of the molecule also tetrahedral. Next one is what? NH3. Lone pair is present here. Lone pair is present. Lone pair present means geometry shape of the molecule is not equal. Geometry shape of the molecule not equal. But how many lone pairs? One lone pair. How many bond pairs? 3 bond pairs. 3 bond pairs nothing but you consider only bond pairs to determine the shape. These 3 bond pairs, if you observe perfectly, the arrangement is like a pyramidal. Arrangement is like a pyramidal. That's why here 3 bond pairs if it is present and 1 lone pair is present, the shape of the molecule is pyramidal. The shape of the molecule is pyramidal because you have to consider to identify the shape of the molecule you have to follow only bond pairs. These are the bond pair, 3 bond pairs like a pyramidal shape. So that's why the shape of the molecule is pyramidal. But here geometry is what? Geometry depend on number of electron pairs. How many electron pairs? 1, 2, 3, 4. Electron pair nothing but bond pair plus lone pair. 3 bond pair, 1 lone pair. Totally 4 electron pair. Electron pairs if it is 4, the geometry is tetrahedral. So here electron pairs how many? 4. 4 nothing but geometry of the molecule is tetrahedral. Here also electron pairs how many? Electron pair nothing but lone pair plus bond pair. How many electron pairs are present? 1, 2, 3, 4. So electron pair 4 nothing but geometry tetrahedral. And here also geometry is what? Tetrahedral. Let us see what is the shape of the molecule. Shape of the molecule depend on only bond pairs. Let us see. These 2 bond pairs you observe perfectly. If you observe, it will be look like a V shape, right? So that's why the shape of the molecule is here V shape. Shape of the molecule is what? V shape. How many bond pairs are present? 2 bond pairs present, 2 lone pairs present. So 2 bond pair, 2 lone pair nothing but shape of the molecule is V shape. 3 bond pair, 1 lone pair nothing but pyramidal. 4 bond pair, 0 lone pair nothing but tetrahedral. So once again, in a molecule there is no lone pair. At that time, shape and geometry equal. In a molecule, lone pairs are present, geometry shape not equal. It is different. So this is the example of CH4, NH3 and H2O. So this is the shapes of the molecule. So let us see different types of the molecules. Let us see here. Different formulas I am taking. Different formulas I am going to identify the geometry and shape of the molecule. It is a very important because every example we cannot explain. So that's why we are taking as a general formulas we are taking. So with the help of general formula we can determine the shape of the molecule and we can determine the geometry of the molecule and examples also. So it is very useful the table. Everyone follows the table and write the notes, otherwise copy the notes. Very important. The table is very important to identify the geometry and shape of the molecule, right? So now here the examples I am discussing. First one I am writing as a formula. In a formula, how many bond pairs present? How many lone pairs are present? At the same time, what is the hybridization? What is the geometry? Next one, what is the shape of the molecule? What is the examples related to it? This is the entire table, right? So here this table is very important. I am going to explain the different formulas. First I am going to explain the formula which does not having lone pair, because we know that lone pairs is not present. Geometry shape of the molecule is equal. Clear? Lone pair is present, geometry shape is different. So first I am going to explain the formula which does not having the lone pairs, right? So for example, the formula I am taking as a formula I am taking AB2. AB2 nothing but A nothing but central atom, B nothing but surrounding atoms. One central atom, around that 2 different atoms are present. For example, BeCl2. For example, what? BeCl2. Otherwise, what? C2H2. BeCl2 and C2H2. For example, BeCl2, if you see, this is the B. Around the beryllium, how many chlorines? 2. So, one central atom, it look like a and these are the surrounding atoms, B and B. Clear? It is like AB2 type of molecule. So for AB2 type of molecule, what is the geometry? What is the shape? Let us discuss. AB2, that means how many bond pairs are present here? See, beryllium chloride, chloride. These are the bond pairs. If there is no lone pair, because beryllium is second group of element, it can be formed the 2 bonds. There is no lone pairs. So AB2 type of molecule, bond pairs are 2, lone pairs are 0. Bond pairs are 2, nothing but hybridization is sp. Hybridization generally we can count number of sigma bonds plus lone pair of electron. Here sigma bonds how many? 2. 2 nothing but sp hybridization. Clear? Next one, geometry. Because we are discussing there is no lone pairs. 0 lone pair nothing but geometry shape is equal, that you can keep in mind. So 2 bond pairs is present, the shape of the geometry of the molecule is linear. At the same time shape also what? Linear. Geometry and shape also what? Linear. So geometry and shape both are equal. What is that here? Linear. Because we are discussing 0 lone pairs. So next example, okay, beryllium chloride completed. So next one is what? AB2 completed. Next one is AB3. AB3 nothing but 3 bond pairs, 0 lone pair, because we are discussing completely 0 lone pairs now. So 3 bond pairs, 0 lone pair, 3 bond pairs nothing but sp2 hybridization, for example BF3. For example BF3, otherwise BCl3. Okay. Boron trifluoride if you see, 1 boron, 1 fluorine, 2nd fluorine and 3rd fluorine. Boron third group of element, valency shell 3 electrons present. These 3 electrons also participating in bond formation. There is no other extra electron. Okay, completed. Next, what is there here? Boron trifluoride nothing but 3 sigma bond. Hybridization is equal to number of sigma bonds, so sp2. What is the shape of the molecule? Trigonal planar. What is the shape of the molecule here? Trigonal planar. Shape and geometry both are equal because there is no lone pair. Trigonal planar. Trigonal planar. Example is what? Boron trifluoride, boron trifluoride. Next one is AB4. AB4 nothing but 4 bond pairs, 0 lone pair. 4 bond pairs nothing but hybridization sp3. For example CH4 we discussed. How many bond pairs here? 4 bond pair, but there is no lone pair. The geometry and shape of the molecule is tetrahedral. Geometry and shape both are what? Tetrahedral. Example CH4 or CCl4. Like we can discuss CH4 and CCl4 and NH4 plus, that is also. Next one is AB5. Next one is AB5 nothing but 5 bond pair, 0 lone pair. 5 nothing but sp3d. So when 5, 4, 3, to identify easily, 4 bond pairs nothing but p orbitals how many? 3. S orbital how many? 1. 3 plus 1, 4 equal. Next one more is what here? One more is 5. That means d orbital 1, 3 orbital, p orbital 3, 3 plus 1, 4, 4 plus 1, s orbital 5. Total how many orbitals are there? 5 orbital. S orbital is 1, p orbital 3 and d orbital is 1. Total how many? 5 orbital. So the bond pairs are 5 nothing but the hybridization is sp3d. There is no confusion, number of bond pairs is equal to number of orbitals. So sp3d nothing but, for example, I am taking PCl5 because 5 bond pairs are present. Phosphorus pentachloride. So for example, the structure phosphorus pentachloride, this is the structure of the phosphorus pentachloride. We can say this is trigonal planar. What is the shape of the molecule here? Trigonal planar, and geometry also trigonal planar because there is no lone pair. What is that? Trigonal planar. Sorry, trigonal bipyramidal. Trigonal bipyramidal. Next one. So AB6. Next one is AB6. 6 bond pair, 0 lone pair. 6 bond pair nothing but sp3d2 because d orbitals 2, p orbital 3, 3 plus 2 5, 5 plus 1 6, sp3d2. So the geometry of the molecule octahedral and the shape of the molecule also octahedral. For example SF6, around the sulfur 6 bonds are present. Sulfur 1, 2, 3, 4, 5, 6. This is what? Octahedral. Next one is AB7. AB7. 7 bond pairs present, 0 lone pairs present. The geometry sp3 d3. Example pentagonal bipyramidal. Geometry and shape of the molecule pentagonal bipyramidal. Example IF7, iodine heptafluoride. Iodine heptafluoride. So this is some examples, formulas and bond pairs and lone pairs. And next one what? Hybridization. And the next one geometry and shape of the molecule and related examples. So this is the table, very very important table here. So this is what? Different examples, right? So this is what when there is no lone pairs. Let us see here. Is any lone pair is there? Lone pair 0, 0, 0, 0, 0, 0. But bond pairs, 2 bond pair, 3 bond pair, 4 bond pair, 5 bond pair, 6 bond pair and 7 bond pairs. When bond pairs are present but there is no lone pair, at that time this is the geometry and shape of the molecule. Next, if lone pairs are present, we know that if lone pairs are present, the shape of the molecule is different. Then what type of shape of the molecule and what is the geometry of the molecule will be discussed. So now this is the entire topic, and once again This is with there is no lone pair. Now we are going to discuss with lone pairs. We are going to discuss with the lone pair. At the time, geometry and shape of the molecule will be changes. Geometry and shape of the molecule is different because lone pairs are present. If lone pairs are not present, the geometry and shape of the molecule is equal. If lone pairs are present, it is not equal. So let us see here. First what? Formula. First what? Formula. Next same bond pairs. Next lone pairs. Next one is hybridization. Next one is geometry. And the next one is shape of the molecule. And the next one is examples. Okay, this is the table. So next here number of lone pairs is present. So if you remember this order, it is very helpful to you and easily we can remember. Because first one, there is no bond, lone pairs. What is that? AB2, AB3, AB4, AB5, AB6 and AB7. Continuously we can remember that. Now what here? With the lone pairs. Now we are discussing with what? Lone pairs we are discussing. So now here, first one, AB to E1. B nothing but bond pair and E nothing but lone pairs. AB to E1 means one lone pair is present here. Two bond pairs present, one lone pair is present. For example, two bond pair, one lone pair, nothing but example is SO2. Example what I am taking? SO2. For example, SO2 I am taking sulfur. Sulfur 6th group of element and it can be formed the 6 bonds, but only 2 oxygens are present. This is and 1, 2, 3, 4. 4 electrons are involving in the bond formation. More 2 electrons are present. The 2 electron not involving in the bond formation means pair. So how many bond pairs? 2 bond pair, 1 lone pair. So valence electron pair repulsion theory, according to this, multiple bond also you have to considering as a single bond. So how many here? 2 bonds. That's and here what? 1 lone pair. 2 bond pair, 1 lone pair. That is what? 2 bond pair, 1 lone pair. Example is what? SO2. Right. So now we have to discuss here. 2 bond pair, 1 lone pair. So bond pairs how many? 2. Lone pairs how many? 1. Hybridization. Hybridization involving number of lone pair plus number of bond pairs. So that is sigma bonded electrons. Now how many bond pairs here? 2. How many lone pairs here? 1. 2 plus 1 is what? 3. So now 3 nothing but what is the hybridization? sp2. And the geometry of the molecule. Geometry of the molecule depend on number of electron pairs. How many electron pairs are there? 3. Electron pair nothing but bond pair plus lone pair both will come. Electron pair nothing but bond pair plus lone pair. Both we call as electron pair. To identify the geometry, we have to count the bond pairs how many, lone pairs how many. So total number of bond pair plus lone pair is equal to, we can determine the geometry. Bond pairs are 2, lone pair is 1. Totally 2 plus 1, 3. Now when the electron pairs are 3, then the geometry of the molecule is trigonal planar. Geometry of the molecule is trigonal planar when 3 electron pairs are present. Next one, shape of the molecule. Shape of the molecule, what here? 2 bond pairs, 1 lone pair is present, right? 2 bond pairs, 1 lone pair is present. 2 bond pair, 1 lone pair is present. The shape of the molecule is bent shape. The shape of the molecule bent shape. See here, bond pairs and lone pair present. If the bond pair, lone pairs is not present, at the time geometry shape will be equal. But a lone pairs are present. Due to the lone pairs are present, the geometry shape will be different. Geometry is what? Trigonal planar. Shape of the molecule is what? Bent shape. Due to the lone pairs are present. If lone pairs are present, geometry shape not equal. If lone pairs are not present, only bond pairs are present, geometry shape both are equal. Now, so next one is what? AB to E1 completed. Next one is AB to E2. Next one is AB to E2. Bond pairs how many? 2. E2 nothing but lone pairs how many? 2. 2 bond pair, 2 lone pair. Total number of electron pairs 4. 4 nothing but sp3. sp3 nothing but geometry tetrahedral. It is fixed. sp3 hybridization nothing but geometry tetrahedral. Shape of the molecule. How many bond pair? 2 bond pairs and 2 lone pair. For example, H2O. Hydrogen and hydrogen. 2 bond pairs are present and 2 lone pairs are present. When 2 bond pair, 2 lone pairs are present, the shape of the molecule is V shape. Shape of the molecule V shape. Example H2O. This is what shape of the molecule. Because of lone pairs are present, the shape of the molecule has changed. Next one. Next is what? AB to E1 completed, AB to E2 completed. Next one, AB3. Next one is AB3 E1, 2 2 will come. AB to E1, AB to E2, 1 category. AB3E1, AB3E2, AB4E1, AB4E2, AB5E1, AB5E2. So it is remembering easy if you remember if you follow this way. So AB2E1, AB2E2 completed. Next one AB3E1, AB3E1, AB3E2 will be there. What is that? AB3E1 is there and AB3E2 is there. Let us see. AB3E1 nothing but 3 bond pairs, 1 lone pair. AB3E2 nothing but 3 bond pairs, 2 lone pairs. Next one 3 bond pair, 1 lone pair, 3 plus 1, 4. 4 nothing but hybridization, sp3. sp3 hybridization nothing but geometry, tetrahedral. Next shape of the molecule. Let us see how many bond pair, 3 bond pair. How many lone pair, 1 lone pair. Example is NH3, CF. How many bond pairs, 3 bond pairs. Clear? Lone pairs how many, 1. Now what is the shape of the molecule? Shape of the molecule is depend on the bond pairs. 3 bond pairs if you see, it is a pyramidal shape. So at the time the shape of the molecule is pyramidal. Shape of the molecule is pyramidal, and example we can give as a NH3, one of the example you can give. Next one AB2E2. AB2 nothing but how many bond pairs, 3. How many lone pair, 2. 3 plus 2 nothing but 5. 5 nothing but sp3d. sp3d hybridization. sp3d hybridization means geometry trigonal bipyramidal. Geometry same, sp3d hybridization nothing but geometry trigonal bipyramidal. Trigonal bipyramidal completed. Then shape of the molecule is what? 3 bond pairs, 2 lone pairs are present. 3 bond pair, 2 lone pairs are present. For example, I am taking ClF3. For example, I am taking ClF3. Let us see the ClF3 structure. Chlorine 7th group of element, valency shell 7 electrons are present. Out of 7 electron, 3 fluorines are forming the bond. That means out of 7 valence electron, how many valence electron participated in the bond formation? 3. Remaining how many valence electrons present? 4. Because chlorine valency shell 7 electron present. Out of 7, 1, 2, 3 completed. Remaining 2 is present. The remaining 4 electron present. The 4 electron presenting as a 2 lone pairs. This is the 2 lone pairs. If we see the structure of this molecule, see here. This is like T shape. Clear? This is what shape? T shape. Like a T shape it is present. So now the shape of the molecule is a T shape. Geometry trigonal bipyramidal. Shape of the molecule is a T shape. Example ClF3. This is what? AB2E2. So AB2E1 completed, AB2E2 completed. AB3E1 completed, AB3E2 completed. Next what? AB4E1, AB4E2. Next one is what? AB4E1. AB4E1. Next one AB4E2. Right? So AB4E1 and AB4E2. AB4E1, AB4E2. Let us see that. Bond pairs how many? 4. Lone pairs how many? 1. AB4E2, 4 AB4, 4 bond pair, E2 nothing but 2 lone pairs. Clear? So 4 bond pair, 1 lone pair nothing but total number of electron pairs 5. Here also total number of electron pair 5. 5 electron pairs nothing but the geometry, the hybridization sp3d and the geometry trigonal bipyramidal. Geometry trigonal bipyramidal, because geometry depend on number of electron pairs. Here also 5 electron pair, here also 5 electron pair. There may be lone pair, there may be bond pair, whatever it. But total number of electron pairs, if it is 5, the geometry trigonal bipyramidal. Here 3 plus 2, 5. Here 4 plus 1, 5. 5 electron pairs nothing but trigonal bipyramidal. So here also geometry trigonal bipyramidal, here also geometry trigonal bipyramidal. But shape is different, because here 1 lone pair is present, here 2 lone pairs are present. And here 3 bond pair, here 4 bond pairs. Let us see what is the shape of the molecule. For that, example. For the AB4E1, I am taking the example is a sulfur tetrafluoride I am taking. Sulfur tetrafluoride I am taking the example. Let us see that sulfur tetrafluoride. Sulfur 6th group of element. Sulfur 6th group of element, and it is a valence shell 6 electrons are present, but out of 6 electrons, 4 electrons are participating in the bond formation. 4 electrons are participating in the bond formation, right? 1 electron, 2nd electron, 3rd electron, 4th electron. Sulfur how many electrons participated? 4 electrons are participated. But sulfur which group of element? 6th group. Mean remaining 2 electrons are present. The 2 electron present as a 1 lone pair. Clear? So we can say this is the seesaw shape. What is the shape of the molecule? Seesaw. Otherwise simply we can say K shape also. K shape. For example, this is a straight line, this is, and we can say as a K shape. Otherwise pi bond also, pi bond how it is present, this is like this only, you can write as a this K shape, otherwise pi shape, otherwise generally we are using it is a seesaw shape. Example is what is the shape of the molecule? Seesaw shape. Example is what? SF4. Seesaw shape also you can say, otherwise K shape, otherwise pi shape also we call. That is next what? AB4E2, 4 bond pairs, 2 lone pair, nothing but 6 electron pairs, 6 electron pair, nothing but sp3d2, because 2 d orbital, 3 p orbital, 3 plus 2 5, 5 plus 1 6, totally 6. Okay, 6 electron pairs are present. 6 electron pair, nothing but what is the geometry? Octahedral. 6 electron pair, nothing but geometry octahedral, or sp3d2, nothing but geometry octahedral. But lone pairs are present. If the lone pairs are present, geometry shape of the molecule is not equal. Let us see what is the shape of the molecule. 4 bond pair, 2 lone pairs. Example, I am taking xenon tetrafluoride. I am taking. For example, if I am taking xenon tetrafluoride, let us see the structure of the xenon tetrafluoride. Xenon 8th group of element. Valence shell 8 electrons are present. Out of 8 electrons, 4 electrons are forming the bond with xenon. 4 electrons of the xenon forming the bond with fluorines. The remaining how many electrons are present? This is the xenon electron, it is the xenon electron, it is the xenon, it is the xenon. Xenon 8th group of element, 8 electrons are present, but 4 electrons only involving the bond formation. Remaining how many electron? 4 electron. Right? 4 electron nothing but 2 electron pairs. So 1 electron pair is above and 1 electron pair is below. This is the shape of the what molecule which is having the hybridization sp3d2 when 4 electron pair, 2 lone pair. We can say this is square planar. What is the shape of the molecule here? Square planar. So the shape of the molecule is a square planar. When 4 bond pair, 2 lone pairs are present, the shape of the molecule is square planar. Example XeF4. And the next one is AB4E2 completed. Next one is AB5E1. AB5E1. That means 5 bond pairs, 1 lone pair. The geometry sp3d3. Because totally what? 6. 5 plus 1 6. 6 nothing but geometry sp3d3. Geometry sp3d3 nothing but here the hybridization sp3d3 nothing but the geometry is pentagonal bipyramidal. Pentagonal bipyramidal. Here this is the pentagonal bipyramidal. Example, 5 bond pairs, 1 lone pair, right? So example I am taking as a XeF5 we can take. Same example, but XeF5. First fluorine, second fluorine, third fluorine, fourth fluorine and fifth fluorine, 1 electron pair is present. This is XeF5. We can say this is square pyramidal. We call the shape of the molecule is square pyramidal. One is square planar completed. Next one is square pyramidal. Example is what? XeF5. Square pyramidal. So this is the what? Formulas. At the same time, number of bond pairs and lone pairs also. So this is the hybridization and the geometry of the molecule and the shape of the molecule. At the same time, AB7 also present. Okay, so this is enough now. Up to here enough. So formula AB2E1, number of lone pairs 1, 2, 1, 2, 1, 2, 1, 2. So now here we can understand from this very clearly. The central atom if does not have in the lone pair, at that time geometry shape of the molecule is equal. If central atom having the lone pair, then geometry shape of the molecule is unequal. At that time, how many bond pairs are present, how many lone pairs are present, and you have to arrange the structure, we can get the shape of the molecule. So this is entire information given by the Valency shell electron pair repulsion theory. So Valency shell electron pair repulsion theory very successful to give the shape of the molecule. So this is the entire chart with 0 lone pair of electron with lone pair of electron. So once you take the screenshot. Clear? So next concept is, so after that we will discuss some questions. Related questions will be discussed based on the hybridization and based on the Valency shell electron pair repulsion theory, because the problems are, the application type of questions are very important, because in the exams such type of application question they can ask except the theory part, right? So now we will discuss some questions here. So let us see the questions. Everyone follows the questions, very important these questions for the competitive exams. First question is number of hybrid and unhybrid orbital in ethane. Question I am writing, number of hybrid and unhybrid orbitals. Number of hybrid and unhybrid orbitals in ethane molecule. In what? ethane molecule. So number of hybrid orbital, number of unhybrid orbitals in ethane molecule. So then what is the hybrid orbital, what is unhybrid orbital, right? So but before we discussed about only hybridization, and hybridization we did not discuss, just valence electron pair repulsion theory we discussed, because hybridization is the entire theory part, so there is no much to discuss, because you can understand hybridization easily. That's why I did not explain the hybridization part, directly entered the valence electron pair repulsion theory. So if you understand the hybridization, we can do the question, what is the hybrid orbital, what is unhybrid orbital, even though I will give the one formula. Based on this formula, we can understand easily how many hybrid orbital, how many unhybrid orbital in a given molecule. The formula is very, very important. So number of hybrid and unhybrid orbitals in ethane molecule. So first let us see that ethane molecule structure. Ethane nothing but CH3, This is the ethane molecule, and 2 carbons are present, and how many hydrogens are present? 6 hydrogens are present. This is the ethane molecule. So number of hybrid and unhybrid orbital, how can you find? So what is the formula to identify that? Number of hybrid orbital. Number of hybrid orbital. So how can you identify number of hybrid orbital? Number of hybrid orbital is equal to sum of all the orbitals in an atom. Sum of all the orbitals. Otherwise, you can take the hybridization also. This carbon hybridization is what, and the second carbon hybridization is what? We can say sum of all hybrid orbitals. Sum of all the hybrid orbitals. Sum of all the hybrid orbitals in atom. Number of hybrid orbitals if we count, that is what? Hybrid orbital. And next one, number of unhybrid orbitals. Number of unhybrid orbitals. Number of unhybrid orbital. Number of unhybrid orbital nothing but number of hydrogen atom, otherwise other than carbon atom, simply we can say that. So other than carbon atom, how many is present here? 6 atoms are present. So number of atoms other than carbon. Number of atoms other than carbon. Number of atoms other than carbon plus number of atoms other than carbon plus 2 into pi bonds. 2 into number of pi bonds. So that is the formula, 2 into number of pi bonds. So let us see. In this question, how many bond pairs, how many hybrid orbital, how many unhybrid orbital asking. So how can you find the hybrid orbital? Sum of all the hybrid orbitals in the atom. Sum of all the hybrid orbital. That means hybridization you have to find. That's hybridization is equal to sum of the sigma bonds plus lone pairs. Here any lone pair is present? No lone pair. Only sigma bonds are present. Around this carbon, how many sigma bonds? 4 sigma bond. 4 sigma bond nothing but hybridization sp3. This carbon having 4 sigma bond. 4 sigma bond nothing but hybridization sp3. Clear? How many sp3 orbital? 2 sp3 orbitals. 2 sp3 orbital. Once you see the sp3, how many hybrid orbitals are present? S, 1 orbital. And p orbitals how many? 3. Totally 1 sp3 nothing but 4 hybrid orbital. 1 sp3 nothing but 4 hybrid orbital. 1 s orbital, 3 p orbital. 1 sp3 nothing but 4 hybrid orbital. Such sp3 is how many? 2. That means 2 into 4, here 8 hybrid orbitals are present. How many hybrid orbital? 8 hybrid orbitals. Next, unhybrid orbital. What is the unhybrid orbital formula? Number of atoms other than carbon. Other than carbon, how many hydrogens? How many hydrogens are present? 6. Plus 2 into number of pi bonds. Anywhere pi bond is present? No. That means 0. It means is equal to what? 6. So number of unhybrid orbitals how many? 6. Number of hybrid orbitals how many? 8. Then number of hybrid orbitals is 8. Number of unhybrid orbitals is 6. This is the answer. Number of unhybrid orbitals how many? Number of hybrid orbitals how many? So we can identify by this formula. Number of hybrid, number of unhybrid orbital. Clear? So next question. Copy this one. Very important. Next one. Hybridization. Next one. Hybridization of the different molecules. How can you identify the hybridization? Already we given the one formula, but you have to do the more number of questions to understand. Hybridization of atomic orbitals of nitrogen. Hybridization of nitrogen. In hybridization of nitrogen in NO2 plus, next NO3 minus, and next one NH4 plus. In these 3 molecules, what is the hybridization of nitrogen? So such type of question they can ask, what is the hybridization in the given molecule, and what is hybridization in the carbon compounds, that when you go to the organic chemistry we can understand clearly. So now here number of what is that hybridization in nitrogen in different molecules they are asking. So let us see hybridization, what we given the formula, Z is equal to half into number of valency electrons of central atom. What is the central atom? Everywhere nitrogen, 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 plus negative charge minus positive charge plus number of monovalent atoms, plus number of monovalent atoms. This is the formula to identify the hybridization. So by using this formula we can identify the hybridization of the molecule, right? So now here let us see NO2 plus. I am going to identify the hybridization of NO2 plus. NO2 plus half into central atom is what? Nitrogen. Nitrogen, which group of element? Fifth. That means valence shell 5 electrons present. Plus any positive charge? Yes. Any negative charge? No. Negative charge is there. How many negative charges? We write plus negative charge. Positive charge is present, minus positive charge. How many positive charges? 1. That means minus 1. Plus number of monovalent atoms. How many? No monovalent atom. Monovalent atoms means what? Hydrogen, fluorine, chlorine, bromine, iodine. That is monovalent. No monovalent, no negative. So that's why no need to take. 5 minus 1 nothing but 4. 4 by 2 nothing but 2 will come. So 2 nothing but hybridization is what? Sp. So NO2 plus hybridization is Sp. Next one is what? NO3 minus. NO3 minus half into nitrogen, fifth group of element, 5 valency electron, minus charge is present. Negative charge nothing but you have to write as a plus negative charge. How many negative charge? 1. It means plus 1. Any positive charge? No. Any monovalent atoms? No. At the time 5 plus 1 6, 6 by 3 nothing but 6 by 2 nothing but 3, 3 nothing but hybridization is what? Sp2. Next one is what? NH4 plus. NH4 plus half into nitrogen, fifth group of element, plus positive charge nothing but you have to write as a minus 1, but there is no lone pair of electrons. At the time 5 minus 1, sorry, lone pair of, so monovalent atoms are present. How many monovalent atoms? 4 plus number of monovalent atoms. Nitrogen valence shell 5 electron minus plus negative plus charge is present, that means minus 1. Number of monovalent atoms 4. 5 minus 1 4, 4 plus 4 8, 8 by 2 4. So it means equal to 4, 4 nothing but Sp3 hybridization. So this is the hybridization we can find by this formula. So nitrogen hybridization in NO2 plus Sp, nitrogen hybridization in NO3 minus Sp2, nitrogen hybridization in NH4 plus Sp3. So we can find this formula, right? So once you take the screenshot. Next one. Which of the molecule has a T shape? Next question is which of the molecule has T-shaped molecule? Which of the molecule has T shape? Which of the molecule has T shape? Which of the molecule has T shape? So T-shaped molecule we have to identify. So options is given. First option is SCl4 and the second option ClF3 and the third option I3 minus and the fourth option is ICl5. This is a molecule. We have to identify what? T-shaped molecule. So we discussed the T-shaped molecule. T-shaped nothing but how can write? One central atom, bond pairs are 2 and here one bond pair. This is like T-shape, right? I given this is like a T-shape. And how many lone pairs are present here? 2 lone pairs. This is a complete T-shape. This is the T-shape. T-shape nothing but you can understand now. How many bond pairs are present? 3 bond pairs. And how many lone pair? 2 lone pair. 3 bond pair, 2 lone pair nothing but it's the T-shape. So if you want to see clearly you can see here. This is one lone pair, another lone pair, here this is. So 1, 2, 3. Clear? So this is what shape of the molecule? T-shape. T-shape nothing but how many bond pair? 3 bond pair. How many lone pair? 2 lone pair. So the molecule which is having 3 bond pair, 2 lone pair, that is the T-shape. So now we can identify T-shape which is having 3 bond pair and 2 lone pairs, right? Sulfur, 6th group of element, valence shell 6 electrons are present. Out of 6 electrons, chlorine forming the 4 bonds. Sulfur valence shell how many electrons? 6 electron. 1, 2, next of all what? And 3, 4, 5, 6. For example, sulfur valence shell 6 electron present. Out of 6 electron, chlorine how many? 4. That means chlorine form the chlorine monovalent atom. Fluorine, chlorine, bromine, iodine monovalent atom, they can form the one bond. So that means here chlorine forming, here chlorine forming, here chlorine forming, here chlorine forming. The remaining how many electrons are there? 2. It is not involving in the bond formation, nothing but lone pair. How many lone pair? 1 lone pair. But T-shape nothing but what is that? 3 bond pair should be present and 2 lone pairs are present. 3 bond pair and 2 lone pair, nothing but that is a T-shape. But here how many lone pair? 1 lone pair is present. So it means this is not a answer, right? Next one, ClF3, chlorine 7th group of element. And 7th group number 7 valence electron, 1, 2, next one 3, 4, 5, 6, 7. Fluorines how many? 3. 3 fluorines forming the 3 bond because fluorine is a monovalent atom. Now how many lone pair? 1 lone pair, 2 lone pair. Then how many bond pair? 3 bond pair. How many lone pair? 2 lone pair. 3 bond pair, 2 lone pair, nothing but shape of the molecule is what? T-shape. So that is your answer. So 3 bond pair, 2 lone pairs is nothing but shape of the molecule is what? T-shape. So this is the T-shape of the molecule. Which of the molecule having the T-shape? This molecule having T-shape. And the next question is hybridization involved at chlorine atom. Hybridization of chlorine. Hybridization of chlorine in ClO minus, ClO2 minus, ClO3 minus. ClO minus, ClO2 minus, ClO3 minus and ClO4 minus. What is the hybridization in this? Same formula, hybridization nothing but half into number of valence electrons of the central metal atom plus negative charges minus positive charges plus number of monovalent atom. Let us see. Z is equal to half into chlorine. I am taking ClO I am taking. For example, I am going to find ClO minus. Valence electrons of chlorine how many? 7th group of elements. So 7 valence electron plus negative charge present, 1 negative charge. 1 negative charge nothing but plus 1. No positive charges, no monovalent atoms. That's why no need. 7 plus 1, 8. 8 by 2, 4. 4 nothing but sp3 hybridization. So ClO minus is sp3 hybridization. Then come to the ClO2 minus. Come to the ClO2 minus. Come to the ClO2 minus. When you discuss the ClO2 minus, half into chlorine 7th group of element, valence 7 electrons plus 1 negative charge, that means positive. No monovalent atoms and no positive charges, that means 7 plus 1 8, 8 by 2 4, 4 nothing but sp3. Next one, ClO3 minus half into chlorine 7th group of element plus 1 negative charge, there is no monovalent atoms, mean 4 sp3. Next one, ClO4 minus, Z is equal to half into chlorine 7th group of element, valence is 7 electrons plus 1 negative charge, 7 plus 8, 8 by 2 4, 4 nothing but sp3. So everything is having sp3 hybridization here. ClO minus sp3, ClO2 minus sp3, ClO3 minus sp3, ClO4 minus sp3, every atom is having sp3 hybridization. So this is the mainly we can identify the hybridization by this formula. At the same time, shape of the molecule also we can determine. T shape is what, square pyramidal is what, square planar is what. So the entire table what I explained here, the entire table is very important to identify the shape of the molecule in geometry. So this is the topic and the today topic, Valency shell electron pair repulsion theory. If you have any doubts, you can keep in the comment section, or if you need any particular topic, also keep in the comment section. We will be discuss the particular topic in the next class. I'll try to complete the topics is very fast because we don't have the time to prepare for the exams. So we have the only less time. So but the topics is going very slowly. So I try to make the fast the topics. So don't skip the topics here, and 55 minutes, 1 hour or 1 hour 10 minutes, whatever the video I am making, if you are watching, if you are a student and if you are preparing for the competitive exam, then listen every topic clearly and you can get the good information compared to textbook and whatever it. So this is a complete information about the Valency shell electron pair repulsion theory, and my name is Venkatesh, and this is the complete Valency electron repulsion theory. If you need any particular topic, you can keep in the comment section. Thank you.